Welcome to this lecture on applied statistics. Today we will talk about analysis of variance and cover chapter 13 and the first parts of 14 in this book by Walpole, Myers, and Ye. Analysis of variance is a lot about comparison of group responses. And in this table, we see the heart rate response in 4 different groups, where the groups differ in smoking habits. And we will denote the response by YIJ, where the subscript I is indicating group, and the subscript J is indicating the individual in that group. And we see that this individual marker can differ between the groups, but in most cases we will say that this number of individuals per group is the same, equal to n. Okay, the question is then if there's a difference in the group, and can we reveal this difference by studying the variability in the groups and between the groups. So we can take averages in the groups, and then we can compare these averages with the grand average. And we can also compare the average with the different response variables in that group. And in analysis variance, there's a lot of dot notation. And here you see the overall mean, where we use notation dot here, y bar dot dot. This is the average over all variables, where we take the sum over all variables and divide on the number of variables. The other mean we take here is the group mean, and then we just have a dot on the second index because we sum over the individuals in the group and average those. And the big question that we're looking at here is to study then the variability within the groups. So within one group, what's the variability here? Within this group, what's the variability? This is the within group variability. But then there's also a variability between groups. And this is then the difference between these means. And by looking at the difference in this kind of variability, we can check if there's a significant difference in the mean between the groups. And that's of course interesting, because if there's no difference between the groups, they can just be merged. We don't need to study the groups differently. Or maybe some groups can be clustered, whereas others cannot be clustered. So these are the questions analysis of variance are trying to answer. Okay, the modeling for this is just like in regression analysis. We say that the response variable is having a mean. This is the group mean. And then we have a residual term. And this residual term is here Gaussian distributed with the same variance. So this epsilon ij is IID normal 0 sigma squared. So it's IID. It does not differ between the different individuals, and it does not differ between the different groups. That's an assumption. And then the key hypothesis here, before you go on and do something more sophisticated, is to check if you can merge all groups. So this is the hypothesis H0, saying that all mean values are the same. That means the mean response in all groups is the same. And we would reject this if there's a substantial difference in the group means, at least compared with the variability within the groups. So that's where this variability comparison comes in. So analysis of variance is trying to break down the total sum of squares into components that is the between group variability so that's called SSA here, the treatment sum of squares. So what is the effect of these groups or the different treatments I? Is it giving a big difference between the means? And then this one is the within group variability. And of course, in some cases, we could have one very small and the other very large, but then they would sum up. And this is the magic rule that we also had in linear regression, that we saw that we could split this sum of squares in different components. So here, what is really happening, what could happen here? Let's say that we have groups 1, 2, 3, and in one case, we have these response variables. This is y, I, j. Let's say we have this response. So here there's apparently small within group variability, but there's quite a large difference between the means in each group. So that means in this case, the SSE would be relatively small, but SSA would be relatively large. An alternative case is to have large variability in the groups. So here there's a large variability. Here maybe slightly smaller, but still large. So here there seems to be some difference between the means, but not significant maybe because there's so much within group variability. And this is what we're then trying to address when we look at the total sum of squares and split it in the different components. And this can be formalized in a Fisher test or an F test, if you like, where we take this sum of squares, where we look at the variability between groups and then normalize it with its degree of freedom. And here we get k, which is the number of groups, minus 1, because we compensate for taking the grand average or comparing against the grand average. And then we divide this by SSE, which is the within group variability, and normalize that appropriately. And these will then be chi-square distributions divided on their degrees of freedom, and this is Fisher distributed. And in such a setting, we would then reject the hypothesis here if we get a large value of the Fisher distribution. So here's a sketch of the Fisher distribution. Here there's a percentile in the Fisher distribution, such that the area here is alpha, the significance level. And this would, if this F statistic is large and ends up here, we reject the hypothesis H0, because such a large F would indicate that there's a significant difference between the group, and then we cannot stick with H0. The difference between the groups is substantially large compared with the variability within the groups. Right, so this is something we can do in software, and here's a Minitab plot where we did this comparison for the smoking example or the heart rate examples with smokers, and we get a F value of 6.12, and the chance of having such a large F value is really small. So here's the F distribution. We had this alpha, which is typically 0.05. And then here we see that we get something here. This is our F. And the chance of having something this large or larger is the p-value. And this is very small, just 0.004. So here we would then reject H0. It's very surprising to get such a large value. And we can also do this in Minitab. So I have this example here. Then we go on stat. We go on ANOVA. one-way analysis. We'll later get to two-way analysis of variance. And here I have the response data in separate columns, and I picked these responses, and I can just press OK. And then I get something out. This is the analysis of variance, where we've split the factor effect, SSA, and it's on its 3 degrees of freedom. There were 4 groups, but this is like k minus 1, and we get this sum of squares that sum to 3000. That's the total sum of squares, and we see these adjusted sum of squares divided on their degrees of freedom, and the F statistic, which is then surprisingly large. So quite easy to do this in Minitab. So we can do another quick example. This is moisture absorption in concrete, where we have K equal 5 groups. And we again do this hypothesis test if the groups are similar or if they are different. This is hypothesis 0 is saying that the groups are the same. They can just be merged. So here we do again compare the within group variability with the between group variability. And we see that the F value comes out quite large. It has a p-value which is small. So we again say this is a small p-value. And we reject H0. And in such a case where you reject H0, you might go on to do more nuanced hypothesis tests. So for instance, here it might seem that this cement aggregation number 4 is down here, whereas the rest are maybe more or less the same. So then we could go on and test, okay, is it such that 4 separates from the rest? And that's another kind of hypothesis test than what we've sketched here. So this is maybe the next level. Right. The sum of squares splits into 2 components. And I thought we could do this calculation to show what is happening here in a simple case. So let's sketch the SST. What was SST? That's the sum over j from 1 to n, sum over I from 1 to k. And in here we have yij minus y dot dot bar. This is the grand average. And in here I can take plus and minus of the group means. That's something that's possible to do. So I'll take this one minus the I dot bar plus I dot bar. Oh, I need a minus on this one. Minus y bar dot dot. I've done nothing so far. The only thing I did was to subtract y dot y bar I dot, so the group mean number I, and I took plus the group mean of y. So I just added 0 more or less. But now I can take this quadratic form and multiply it so that I can split it into the first component and the second component and a cross term. So let's do that. And we can, of course, the sums don't matter here. So we could take I or j first or last, at least as long as n is the same. So now I take ij minus I bar y bar I dot squared. And then we get the second component in the sum. So this is I dot and then y bar dot dot. And then we get a cross term. So that's 2 times the cross terms. J1 to n, k, I1 to k. And now we need the cross term. So this is the first part the difference within group times the difference like this. And this part, what is this? This is the difference from all data to its group mean. So this is actually SSE. And this part is the difference from all the group means to the grand average. So this is the variability between groups, which we called SSA. The tricky part is this thing here at the bottom, which we didn't have. So if we can prove that this thing is 0, we're fine. And this is not so tricky to prove in our case. Let's do that as well. We had the sum over I 1 to k, sum over j 1 to n, and here we had this one, and yij minus yi dot. And why did I write this term before that? Well, I see that this sum over j can actually go inside this first part. So I can take the I sum, so everything depends on I, but this y bar I dot minus y bar dot dot does not depend on j. So now I take this sum of j inside, and then I have the sum over yij minus y bar I dot. And what is y bar I dot? Well, that's 1 over n, and then we sum over j, yij. And this means that we can also write things differently. So what do we have here? Well, this is the sum over yij, and then minus n times this sum. And n times this sum is just the sum here. So this is then the sum over yij, and then actually minus this sum, which is 0. So we see that the cross term cancels, and we're left with these two components, and that's SSE plus SSA. So it's a relatively easy proof or calculation that shows that the total sum of squares can be split in an within group variability SSE and a between group variability SSA. And this is what we compare in the analysis of variance examples that we saw. Yeah, so this model view can also be looked at in a slightly different way, where we take this grand average, but in a theoretical sense. So we take the mu out, the overall theoretical expected value, mu outside, and then we take alpha I as the difference from this grand expected value. And then we require a constraint here saying that all these differences are equal to 0. And then instead of having a test that the group means are equal, we test that all these departures from mu are equal to 0. So this is a common way of doing this, and especially when we start doing more factors. We can also see this as a regression model where we form a design setting. So what was our model? It's equal to this. So this is our model. Can we write this part as a regression model? Well, we can. So then this one becomes, so what do we have here? We had y1, 1, y1, 2, and then y1, n. And then it continues with y2, 1, y2n, and all the way down to ykn. And we can write this as a design matrix where we multiply with mu, alpha 1, alpha k. and then there's plus an epsilon 1, epsilon kn. And the design matrix in front here then finds the right, of course it always has the mu, so we always need the mean, the grand mean, but then we pick out the right effect. So if this is for the first part is for the first group, so then we need alpha 1, but nothing else. Then we get to the second group, so then we need 0, 1, and then 0 again, and then it continues like this. Here we get only the alpha k variable. So there are many ways of looking at analysis of variance, and one way is better sometimes, another way is better sometimes. Some are easier to interpret, some are easier to calculate, and so on. Yeah, so this whole business of analysis of variance has been very important to pioneer the effort of randomized designs. And in particular, when Fisher looked at this 100 years ago, he studied agricultural businesses, and then he saw that it was really important to use blocks because blocking errors or problems with blocking sort of were hiding the main effects that he were interested in. So instead of planting just wheat at the lower end and barley at the upper end, perhaps it was good to randomize this to see which type had a better opportunity or to see which opportunities were really there. And if he couldn't block, he randomized over the rest so that you didn't get any effects of the way you set up your experiments. So this has always been very important in the study of analysis of variance. And to see this blocking effect, let's look at something called Simpson's paradox, which is somewhat different but still related to this topic. Let's say we have a sports competition and this is split over 2 days. So it's Saturday and Sunday. And on the Saturday competition, the men score 1 out of 5 trials. So that means they have a success of 0.2. In the Saturday competition, the women score 2 out of their 8 trials. So what's their winning fraction? It's 0.25. And this means that the women win in the Saturday event. And then this sports competition continue on Sunday. And then Sunday, there's something with the conditions. So men do much better. They score 6 out of 8 times. And this is 0.75, a much higher percentage. And the women also do much better. They score 4 out of 5 trials. So this means that their success rate is 0.8 this time. And again, the women win. 0.8 is larger than 0.75. So if we just look at this plot and split the competition in 2 blocks, Saturday and Sunday, women win both times. They have a better success probability. But what if we look at this overall? What happens then? Then we see that the men actually score 7 out of 13 trials, and the women score 6 out of 13 trials. So this means that men win when you look at this combined. And this is a paradox because when you looked at every block, you saw that women won in each block, but overall the men actually win. And the difference is, of course, that the number of trials for men were much higher on Sunday when it seems like the conditions were better. Or and the men had less trials on Saturday when the conditions looked worse. So this is indicating that blocking is important, and we should try to get some kind of homogeneity in our example to study carefully. So the blocking can then be written in an additive way, like we've done here. And then we say that, okay, here there's a grand effect. This is the grand effect that goes for every setup. And then we have this one, which is the treatment effect or the group effect. And then we say that, okay, there's something with the blocks that gives a block effect. Maybe this was Saturday or Sunday or the high hills or the low hills or the weekend or the weekday or night and day. So this is the block effect. And we're not really interested in this block effect, but we like to include it because then we can get better estimates of the treatment effects. So here's an example of blocking where four machines are compared. So this is the treatment variable. We want to compare the different machines, but we have different operators, and these are the blocks. So why do we want each operator to run all these machines? That's a lot of trials. Couldn't we just have use some of the operators here and then spread them out on different machines? Well, it turns out that some operators are better than others for this example. Say operator 6, he's doing pretty well compared with operator 2. He's always better, and for some of these machines, he's very much better. And we could have had another situation too. Let's say that operator 6 is doing better at machine 1, but operator 2 is doing better at machine 4, and that's always a case there. Then there's actually an interaction which is not accounted for in this additive model. But if the operators are sort of better overall than others, and it holds for all machines, then this blocking model that we discuss is good. So in addition to blocking here, we typically have randomization so that the order that all these operators run the machines is randomized. So even though we've structured it like this in a nice table, perhaps operator 1 was actually running machine 4 first or machine 3 first, whereas operator 2 was running machine 1 first, then 4, and so on to get get away from some kind of training in the runs. Again, in blocking, we can split the variance. Here we can split the variance in treatments, block effects, and residual effects or error sum of squares. And then we can study if the treatment effect is significant by looking at this Fisher statistic here at the bottom. And this would be Fisher distributed with k minus 1 degrees of freedom, k minus 1 times b minus 1. So this is the number of treatments minus 1, number of blocks minus 1 that we get here to estimate the variability. And if we do this exercise, we for this machine and operator effects, we can see that we get a Fisher statistic, and we can compare this to do the analysis to see if this is significant or not. What is the p-value? And again, this is an overall hypothesis where we compare all equal. That's our hypothesis 0 against the alternative. And then if you reject this, you can go on to do other hypotheses, maybe. So I mentioned that here we say that the blocks and the treatment effects are additive, so they split. In two-way analysis of variance, this is not the case. So in two-way analysis of variance, you actually say that, okay, you have two factors and you're interested in their main effects and their interaction. And interaction is important in analysis of variance and other branches of statistics, because now you might have different effects, whether you have high or low values for the different factors. let's say this example with energy for engines, and then when you have type A, you might have higher energy for low temperatures, but another kind of engine has higher for high temperature. So then this is opposite, and there's clearly a connection between temperatures and type A and B. And this would not be captured in an additive model like we had for blocks. So you're interested in something more sophisticated. And here's an example where we are interested in both examples or both factors. So here the propellant type is factor B or factor 2, and this one is factor A. And to study all these interaction, we need replicates. So when I say replicate, we need 2 samples here for each kind. So this would be yi, j, where I is for this factor, j is for this factor, and then we had k, where k is 1, 2. That's the replicates here. And since we have replicates, we can estimate all effects and all interaction effects, and we can also say something about the noise in our model. So the model here would be a grand mean and then a main effect for factor 1, a main effect for factor 2, and then interactions between these factors. And then a noise term that we again assume to be independent and normal distributed. And why do we assume this normal distributed? That goes into the Fisher distributions. So if we didn't assume this, we will never get to the Fisher distribution to see if things are actually significant or not. Yeah, so now you see there's a lot of indices here, I, J, K, and if we started to have more factors, it would be I, J, K, L, M, N. So that's a lot of indices. So then you might start doing something different. Say you only have a few levels for these factors. Okay, so now we have again a sum of squares, just like in any other ANOVA or analysis of variance exercise. We split it into a factor A variability, B variability, and then this is the interaction variability. And this interaction variability is often something we want to test here to see if it's significant. And if this is not significant, we can remove the interaction and get a better handle on the main effects. So here's again a test setup where we compute this sum of squares and compare it with the residual error sum of squares. And we can get then different Fisher distributions with its right degrees of freedom. That's how we compare things. And as I said, we would in most cases be interested in checking this. So that means checking if this one is surprisingly large. So if this is large, then you keep interaction terms. If this is small, or that means a hypothesis about 0 interaction cannot be rejected, then we maybe remove the alpha, beta, ij part of model. We say there are no interactions. Interactions are not required here. We only have the main effects. So this can be done in most software types. Here's a analysis of variance table where we see that there is some interaction, but maybe not so much, 0.05 p-value. So that means we are out in the tail, but not very far out in the tail. So it should be discussed. And one way to discuss this or to look at it in more detail is to make plots. And here are main effects plots where we see that for the missile system, factor A, there's clearly a trend of going down, maybe less so going from 2 to 3 than from 1 to 2, or more from 2 to 3 than 1 to 3, 1 to 2. And then in a propellant type, there seemed to be maybe similarity between 3 and 4, but not so much between 1 and 2 and those last two. So these are helpful to see if things are different. And you can do the same for interactions. So then you plot over different levels of missile type or propellant type, and the colors and the different lines indicate high, low, medium, or very low level of these other types. So there are four factors for one of them, and then three levels for the other factor. So combining these things with the analysis of variance table, we might be able to draw some conclusions. And usually if there's no interactions, we would tend to have parallel lines here where the interaction goes up. So this is like parallel lines indicate no interaction. So here they are clearly not parallel, but maybe not that different either. So if you see big interaction, you might see something like this, where the lines go up and down, and there's definitely a difference whether we keep one high and then look at the effect of the other, or if we keep one low and look at the effect of the other. That's what these plots show, interaction plots. Requires some twisting of one's head to get around these interaction parts. Yeah, we mentioned that the replicates can change from groups and factors, so it doesn't have to go always to the equal numbers. We can have two replicates for one combination and three for the other, or five for one. We can still do the analysis. It's just more bookkeeping. Power is important, so we're mainly looking at this hypothesis zero, if it should be rejected or not. Power is important. So we want to reject when H0 is false. That's the power. But remember here that this SSE is always sort of sigma squared related. So it's SSE divided on the degree of freedom is unbiased for sigma squared, no matter H0 or H1 here. This is always providing an estimate for the variability. But if there were no interactions, this one would also quantify the variance. So under the hypothesis zero, this should also be a good way of estimating the variability. But if the H0 is not true, then we study the power, and then we would quickly want to detect that this one is different so that there are significant interactions. And in order to do this, you need to study something called a non-central Fisher distribution, where the numerator is then having a non-central distribution. So we didn't discuss this so much, but this is a topic that's also important for analysis of variance. Yeah, contrasts is the next level. If you reject the hypothesis of equal means, you might go on to test linear combinations. But there are a bunch of linear combinations, so you might want to think carefully about this. Which ones should we test? Maybe for some examples, you see a clear combination you want to test. Say you want to test mu1 plus mu2 minus 2 mu3. Then you compare 2 and 1 with 3. Can they be clustered in this way? But overall, there are many different ways of comparison here. You can test this one all the way down to k minus 1 minus k. Then you tested all singles or pairs. So you can have many tests here. And in the end, one has to worry about the significance level because you do multiple testing. You have to be careful. Contrasts actually get 1 degree of freedom for the numerator. So this is equivalent of testing a two-sided t-test. So the Fisher distribution with 1 degree of freedom and something else in the denominator is equal to a two-sided t-test. And that's what you can see here. If you compute this linear combination, you get a normal distribution, and then you have to estimate the variability. So then it's a t-test. And then a chi-square is a normal distribution squared. So this is how they're connected. As I said, multiple testing is a challenge if you start looking at many contrasts, because if you do a single test, you can easily keep the right significance level. But if you start doing many different tests, you have to worry about your significance level, because if you do many tests, you're very likely to reject one of them or two of them or three of them. So if you do this by looking for a rejection, you're doing the wrong exercise. Don't do that. Then you're sort of hunting for small p-values. So instead, one should try to compensate for the right t-level, and there's many ways of doing this. There's something called Bonferroni tests. There's also other methods here, like Tukey's methods or other alternatives. Something called false discovery rate, where you look at the number of false positives and try to look at that. Okay, so that's analysis of variance. I hope you learned something.